And away we go. Let's show that the relation on the integers times the integers defined by the pair xy is in the relation, in other words, x is related to y, if and only if the absolute value of x is equal to the absolute value of y. Show that this is an equivalence relation and then describe the equivalence classes. So to show that something is an equivalence relation, we'll have to show three things. We'll have to show that it is reflexive, we'll have to show that it is symmetric, and we'll have to show that it is transitive. And let's just recall the definitions of these things. The reflexive condition is that for everything in the set on which we're defining a relation, and in this case, those are the integers. Okay, we have pairs of integers. We're in z times z, but we're asking for one integer to be related to another. So the definition of reflexive would be, for every integer, that integer is related to itself. Symmetry would say, for any two integers, let's call them u and v, if u is related to v, then v is related to u. And transitive would say, for any three integers, let's call them a, b, and c, if a is related to b and b is related to c, then a is related to c. Okay, so here in my handwriting, we're using the notation ZRZ or URV, etc. for the relation. So up at the statement of the problem, we could write this as x is related to y. Okay, this is just slightly less writing than writing out the ordered pair and the set inclusion notation every time. All right, so let's prove these three conditions. First, reflexivity. So here's the definition of what we want to prove. So the first thing we'd say is let z be an integer. We now need to show that z is related to itself. If we can show that z is related to itself, that step will be done. How do we show one number is related to another? Well, let's look at the definition of this relation. Z is related to z, so both of these are z, if and only if the absolute value of the first entry is equal to the absolute value of the second. So back to our problem, what we need to show is that the absolute value of the first number is equal to the absolute value of the second. And since the first and second number are the same, they're both z here, this is transparently true and there's not really any argument to be made. So let's move over to symmetry. The definition is, for any two numbers, the first is related to the second implies the second is related to the first. Notice that the second number here is the first number there, and the first number here is the second number there. So we'd start off by saying, let u and v be integers. We get to assume that u is related to v. We then need to do some work to show that v is related to u, but if we can get there, we'd be done. So what does the assumption that u is related to v get us? Well, the first number is related to the second first number is related to the second, if and only if the absolute value of the first is equal to the absolute value of the second. So from the assumption that u is related to v, we can say that the absolute value of u is equal to the absolute value of v. And what would we like to say in order to claim that v is related to u? We would want that the absolute value of v is equal to the absolute value of u. The question just becomes, here's my given information, what I've assumed, here's what I need to show. How can I argue that if this is true, then so is this? Well, there's really not much to say because the equals sign is symmetric. If the left side is equal to the right, then the right side is equal to the left, and that's all there is to it. Moving on to transitivity, we would say, let a, b, and c all be integers. We get to assume that a is related to b. In other words, the absolute value of a is equal to the absolute value of b. We get to assume that b is related to c. In other words, the absolute value of b is equal to the absolute value of c. What we need to show is that a is related to c. So what we need to show is that the absolute value of a is equal to the absolute value of c. But we also know that the traditional equals sign is transitive. If this equals that, which then equals this, then the first is equal to the third. The equals sign is already transitive, so this relation obviously is as well. So there's not much proof to be done here because this is done using an equal sign, which inherently carries with it a lot of symmetry, transitivity, and reflexivity. Okay, we'll see in the next example that we can construct something where one of these fails, but using an equal sign in your relation is going to save you a lot of work because the equal sign is by definition symmetric, reflexive, and transitive. Okay, so we've shown the three conditions, so it is an equivalence relation. What we now need to do is describe the equivalence classes. So what are the equivalence classes? So the equivalence class of x is by definition all of the integers that are related to x. In other words, it's all of the integers so that the absolute value of z is equal to the absolute value of x. Well, how can two integers have the same absolute value? So it's all of the integers so that z is equal to plus or minus x. In other words, as a set, it's just x and minus x. So if we have the integers listed out, so 0, 1, 2, 3, 4, and so forth, but also -1, -2, -3, -4, and so forth, -4 is in the same equivalence class as 4 because they have the same absolute value. -3 is in the same equivalence class as 3. -2 is in the same equivalence class as 2, -1 is in the same equivalence class as 1, and 0 is just by itself in an equivalence class because plus 0 and minus 0 are the same number. So those are our equivalence classes. They're just pairs of numbers, plus or minus the same integer, except for 0, which is its own equivalence class. Next, we have problem 2. Again, we're looking at a relation on pairs of integers. So when is one integer related to another? If the absolute value of the first is equal to the second. And note now that there's no absolute value here on the second entry. So we're supposed to show this is not an equivalence relation by finding an explicit counterexample that shows it is not reflexive. So to be an equivalence relation, the relation has to be reflexive, symmetric, and transitive. If any one of those fails, then it's not an equivalence relation. This relation is not an equivalence relation, and we're given a fairly big hint that it is not reflexive. So it does not satisfy that for every integer, that integer is related to itself. In other words, it is not the case that for every integer, the absolute value of the first number, okay, here I have the first entry, which has an absolute value, should be equal to the second without an absolute value, and that's just z. So we're claiming it is false that for every integer, the absolute value of that integer is equal to the integer itself. And what we know from how these symbols operate, this means what we're trying to show is that there exists an integer z such that this equality fails. In other words, does there exist an integer z so that the absolute value of z isn't equal to z? Are there any numbers you can think of that have to be integers whose absolute value is not the same number you started with? Sure. There are lots of examples, but if we pick, for example, z equals -246,908, well then, the absolute value of z is 246,908, which isn't equal to the negative version of that number. In other words, is not equal, well here this would be equal, to z. So we have an integer z that isn't equal to its absolute value. Any negative integer other than 0 would have worked here, okay, but I just went with this one. So there is one particular integer that shows this relation is not reflexive, and if it is not reflexive, it is not an equivalence relation. Moving along, we have the relation L, still defined on the integers, and the definition is the integer x is related to the integer y when x is less than or equal to y. We're supposed to show this is not an equivalence relation by finding a counterexample to show that it is not symmetric. Now, symmetry would say that for every x and y in the integers, if x is related to y, then y is related to x. And we want this to not be true. In other words, there should exist x and y in the integers so that this conditional statement fails. Well, how does a conditional statement fail? There must exist x and y in the integers such that the hypothesis is true and the conclusion is false. In other words, x should be less than or equal to y, and it is not the case that y is less than or equal to x. In other words, it is not the case that y is less than or equal to x. And by De Morgan's law, this would mean that y is not less than x, and y is also not equal to x. In other words, y is bigger than x. So our goal is to find the existence of x and y, which are integers, so that x is less than or equal to y, and y is bigger than x. There's lots of ways to do this. For example, if I let x equal 48, and I let y equal, 106, then indeed, is x less than or equal to y? Is 48 less than or equal to 106? Yes. Is y bigger than x? Is 106 bigger than 48? Yes. So for this particular choice of x and y, and again, there's lots of ways you could do it, x is less than or equal to y, but y is not less than or equal to x. In other words, this relation is not symmetric. Moving on, we've got the relation p, still defined on integers, saying one integer is related to another if and only if the distance between the two is less than or equal to 1. In other words, the absolute value of x minus y is less than or equal to 1. So two integers are related when the distance between x and y is less than or equal to 1. We want to show this isn't an equivalence relation by violating transitivity. So here's what transitivity would look like for any choice of three integers, x, y, and z, if x is related to y and y is related to z, then x is related to z. And we want this condition to be false. So we want there to exist a choice of x, y, and z such that the conditional statement fails. In other words, x is related to y is related to z, but x is not related to z. So here we have the hypothesis being satisfied, but the conclusion being false. So what we want is the absolute value of x minus y should be less than or equal to 1. The absolute value of y minus z should be less than or equal to 1, but the absolute value of x minus z is not less than or equal to 1. In other words, it's bigger than 1. And this becomes fairly apparent once you remember that the absolute value of the difference between two numbers is the distance between them. So can we think of integers, x, y, and z, so that x is distance 1 away from y is distance 1 away from z, but x is more than distance 1 away from z? Yeah, all we've got to do is, for example, pick a number for x, 10. Let's let y be 1 smaller than that and z be 1 smaller than that. Then the absolute value of x minus y is the absolute value of 10 minus 9. That's just 1. So 10 is related to 9. However, the absolute value of y minus z is now the absolute value of 9 minus 8, still 1. So 9 is related to 8. The distance between them is no larger than 1. Turning our attention to the third condition, however, the absolute value of x minus z will be the absolute value of 10 minus 8, which is 2. 2 is bigger than 1, so 10 is not related to 8. So this relation is a way of measuring distance, and what we've basically said is two numbers are said to be in this relation if their distance between them is less than or equal to 1. And it's totally possible for one number x to be fairly close to another number y, and for y to be pretty close to the number z, but for x to not be that close to z anymore because the distance have added up. Moving on, we've got problems with functions. So here, f is a function with domain A, codomain B. G is a function with domain B, codomain C. The function h isn't actually going to show up. Show that if f and g are both injective, so is the composition g of f. So we assume that f and g are injective. In other words, f is injective and g is injective. What's the definition of an injective function? So f is a function with domain A and codomain B. The definition of injective is for any two elements of the domain, so the domain here is A. I have two elements, so let's use little a's, but since there's two of them, I'll give them subscripts so that I can tell them apart. So for any two elements of the domain, if I assume that f of one thing is equal to f of the other, then I automatically conclude that the two things I started with are the same. This is the definition of injective. For any two elements of the domain, if the function applied to each of them are equal, notice that f of a1 is not in the set capital A. a1 is in the set capital A, but then the function f takes those things and sends them to the set B. So this is in the set B, this is also in the set B. If these two elements of B are equal, then these two elements from the set A are equal. And the fact that G is injective is pretty similar, but note, what is the domain of G? The domain of G is the set B, so to keep my notation clear, I need two elements from the set B, let's call them little b1 and little b2. If G of b1 equals G of b2, then b1 must equal b2. And let's take a moment to ask what sets these belong to. b1 and b2 are in the set B, but the function g sends the set B into the set C. So this equality is in the set C, whereas this equality is in the set B. Now these are two statements I do not have to prove. This is simply what we were given. We are allowed to assume that f and g are both injective. But now we need to show, so is G composed with f. So we claim that G composed with f is also injective. What's the domain of G composed with f? Well, the first thing I have to do is apply the function f. And the domain of f is the set A. So I'm plugging in things in A. F then sends those to the set B, which can then be plugged into this function g and end up in the set C. So this composition, since I have to start by applying the function f, I have to start with its domain. Since I end with the function g, I end with its codomain, which is the set C. And in order for this composition to even make sense, what we need is some sort of alignment between the codomain of the first function and the domain of the second, so that I can go from A to B and then from B to C. Okay, so we claim that this is injective. In other words, what we claim is that for any two elements of the codomain, of the domain, A1 and A2, if G composed with f of the first one equals G composed with f of the second one, then they must have started out as the same element. And I don't know this yet. Okay, this is what we are claiming. In other words, this is the assertion. And fundamentally, we have asserted a conditional statement. And if we assert a conditional statement, we can try to prove it directly. So let's just start off by assuming all of this. Suppose we have two elements of A, and we assume that this statement here is true. So let A1 and A2 be elements of the set A, then assume that G of f of A1 is equal to G of f of A2. We're doing a direct proof. We've assumed this hypothesis. The only thing we need to do is show this conclusion. So if we ever manage to make A1 equals A2 show up, the entire proof will be done. Okay. We used arbitrary variables here that haven't been used for anything yet in the proof. Up here, this definition, these A's, first of all, they're bound to this quantifier, so they don't really carry any meaning. But also, this is just the definition. This doesn't even need to be written in the proof. Okay. This is just the definition of assuming f and g are both injective. So A1 and A2 are arbitrary elements of the set A, and we've gone ahead and assumed the hypothesis G of f of A1 is equal to G of f of A2. But this can be interpreted as G of f of A1 and G of f of A2. Now suppose I denote B1 to be f of A1 and B2 to be f of A2. Since f takes things from the set A and sends them to the set B, whatever A1 is being sent to, I'm going to call B1. Whatever A2 is being sent to, I'm going to call B2. I'm not claiming A1 and B1 are the same. They're in different sets. That would be ludicrous. But the thing that F sends A1 to, I simply decide to call B1. And if I were to plug A2 into the function f, I call that B2. So then back here, what we have is that g of B1 is equal to g of B2, but we know that g is injective. So if g of B1 equals g of B2, if g of B1 equals g of B2, I can automatically conclude, via modus ponens, that B1 equals B2. So since g is injective, B1 must equal B2. In other words, f of A1 must equal f of A2, because remember, B1 was just the temporary name we gave to f of A1, and B2 was just the temporary name we gave to f of A2. But now, since f is injective, if f of A1 equals f of A2, I can immediately conclude that A1 equals A2. So, since f is injective, I can immediately conclude that A1 equals A2, and we already knew that was where the proof could end. Very similar to the last problem, we want to show that if f and g are both surjective, then so is g composed with f. So again, we're going to go ahead and assume that f and g are both surjective. In other words, f is surjective, and g is also surjective. And the definition of surjectivity is that anything in the codomain is the image of something from the domain. So f, having codomain B, I'd say for anything in the set B, there is something in the domain A so that f of A equals B. Similarly, the definition of G being surjective, well, it has codomain C. So for everything in that set, there must exist something from its domain so that G of B is equal to C. What we're claiming, in other words, asserting, is that G composed with F is surjective. Okay, and remember, just as in the last problem, since F goes from A to B and then G goes from B to C, G composed with F goes from A all the way to C. So this function has domain A and codomain C. So if the codomain is C, the claim is that for every element of the codomain, there exists something in the domain. But remember, the domain of this composition is actually the set A, such that G composed with F of A equals C. And again, I've put this in parentheses to try to highlight, we do not know this is true. This is our assertion. But let's just work through it. It's claiming something universal about the set C. So let's just suppose we have an arbitrary element from the set C. The second part of the claim is just something existential about the set A. So I'm allowed to pick this A to be very specific. Okay. But let's turn our attention back to the set C. We already know that G is surjective. So anytime we have something in C, there must exist something in B so that G of that is C. So I can come back here and I can say, since G is surjective, there exists something in B so that G of B is equal to C. And now what we have is something in the set B. But since F is surjective, anytime you have something in the set B, there is something in the set A so that f of A equals that thing. So we now have something in the set B. So since F is surjective, and little b is an element of big B, there must exist something in the domain of F so that f of A is equal to B. But now let's see what happens. What is G of F of A? Well, it's G of f of A. What was f of A? F of A was B, and what's G of B? Little c. In other words, there is something in the set A so that G of f of A equals little c, where little c was this arbitrary thing we started with. Okay, in other words, we've got A that gets sent to the set B, that gets sent to the set C. This is the function f, this is the function g. Out of this set, I pick an arbitrary little c. But since G is surjective, I know that there's a little b that gets mapped there. And since F is surjective, I know there's a little a that gets mapped there. And overall, the function g of f has started with a and ended with c. And we started with an arbitrary element of c. So everything in c can be hit by the composition g of f. The composition g of f is also surjective. We turn our attention now to negations of similar problems to the ones we just did. Again, we have the function f going from a to b and the function g going from b to c. Show that if g is not surjective, then g of f is not surjective. So assume g is not surjective. Okay, so surjectivity would say for anything in the codomain, there exists something in the domain such that g of b equals c, but we're saying that's not true. So there exists something in C so that for every element of B, g of b isn't equal to c. Okay, so the first thing we do is we push our negation past this quantifier, reversing it from for all to exists. Now I have a negation here. If I push it past that quantifier, this exists becomes for all, and the negation of equals is just how we use this symbol here, the not equals sign. So this is what we get to assume. We now claim, aka assert, that g of f is not surjective. So we claim that g of f isn't surjective. Now here's what g of f being surjective would say. Remember that g of f has domain capital A. And we're claiming that this isn't true. And again, how do we work with this negation? If I push it past this universal quantifier, this becomes existential, and now the negation lives here. If I push it past that quantifier, this becomes universal, and the negation now lives here, and that's just a negated equal sign. So what we are claiming is that there exists something in capital C so that for anything in capital A, g of f of A isn't equal to C. Now, all we need to do is find something in the set C. This isn't an arbitrary element of the set C. This isn't something that's going to apply to everything, just one special element. But we already know there is a special element of the set C. It's special because nothing from B is sent there by the function g. So since g is not surjective, there must exist a special element of C so that for any element of B, g of b isn't equal to c. But now let's see what happens if I pick any element. Sorry, let's cross that out and just say, so now, let A be an arbitrary element of A. We have picked a special element of C, the one that G never achieves. Now I need to account for this universal statement, so let's let little a be arbitrary. Okay. Now, what can you tell me about f of A? It's definitely in the set B. So what we know is that for anything in the set B, g of that isn't C. For anything in the set B, g of b is not C. So here is something in the set B. So g of that isn't C. And we're actually done. Okay, what we are trying to show is that there exists something in C so that for anything in A, g of f of little a is not little c. We picked the special C to be the thing not achieved by the function g. We know that exists by assumption. So there is a special element of C that no matter what we plug into the function g, g of little b will never equal C. Now, no matter what little a you pick, f of a is in the set B, so g of that can't be C. In other words, the composition g of f is not going to be surjective. Continuing along with similar problems, okay, now let's show that if f, the function going from the set A to B, is not injective, then the composition g of f cannot be injective either. So we get to assume that f is not injective. So the definition of injective would mean for any two elements of its domain, let's use little a's for clear notation, and I have two different elements, so let's give them subscripts. For any two elements of the domain of little f, if f of the first one equals f of the second one, then I must have started with the same two things. That would be the definition of f being injective, but we're assuming f is not injective. So we play the quantifier game. A negation of a universal becomes existential, then the negation is here, but that's a conditional statement. The negation of a conditional statement is a true hypothesis, false conclusion. So there exists an A1 and A2 in A such that the hypothesis is true and the conclusion isn't. Okay, so this is not something we need to prove. This is our given. F is not injective. There is a choice of A1 and A2 in its domain, so that f of A1 does equal f of A2, even though I did not start with the same thing. Now our claim is that g of f cannot be injective either. So we claim, in other words assert, that g of f is not injective. So let's see what that is asking us to show. Injectivity would mean, for any two elements of the domain, what's the domain of the composition g of f? The domain is A, so I'll take two elements, I'll call them A1 and A2 again. Plugging them into the composition being equal would imply that they started off equal. Now this is the definition of injective, and we're saying that's not true, but it's in big giant parentheses. We don't know this. This is our assertion. But if we work through what this negation looks like, very similar to before, it would be that there exists an A1 and an A2 in the set A, so that this hypothesis is true, but the conclusion isn't. And again, this is our claim. This is what we are trying to show. The existence of a special pair of elements of A that make all of this happen. So we don't have a lot to go on, I just need to pick two elements of A, but I don't want them to be arbitrary, they should somehow be special. Thankfully, our given is that there is a special pair of elements in A, so I really only have one reasonable way to start this proof. Since f is not injective, there exists an A1 and an A2 in A, so that a couple of things happen. F of A1 is equal to f of A2. A1 is not equal to A2. We've now made our choice of what these two things should be. Now we have to show g of f of A1 equals g of f of A2. A1 isn't equal to A2. Well, we've already got A1 isn't equal to A2. It came right out of our assumption. The other thing that came out was that f of A1 equals f of A2. Well, if those are exactly the same thing, then g of f of A1 has to be the same as g of f of A2. Since f of A1 and f of A2 are equal, if I plug the same thing into the same function, I get out the same result. If these are the same thing, f of A1 is equal to f of A2, and I plug them into the same function, I get out the same thing. In other words, g of f of A1 is equal to g of f of A2, even though A1 was not equal to A2, and that's exactly the definition of showing that g of f is not injective. We found a special pair of elements in A, so that g of f of that pair are the same, but they didn't start out the same. And the special pair that we picked was from our given that f is not injective. There is a special pair of elements in A that aren't the same, but when you run them through the function f, they become the same. And then when you run those through the function g, they stay the same.